And hopefully this will be pretty gentle today. This is not really profound, so that's a good way to start back. All right, this is section 4.4. It's not wanting to focus here. There we go. So we're going to talk more about kind of the span, the generator for a vector space. We're going to start with the definition. Okay, this is a pretty simple definition. If we have a finite set of vectors that will generate a vector space, then it's called finite dimensional. If there's no such set that exists, then it's infinite dimensional. And after we get done with our next definition and some examples, I'll give you an example of each of those types of vector spaces. Definition number 2. Okay, this is the definition of a basis. B-A-S-I-S. And we have actually referred to this before. Remember we talked about the standard basis vectors for Rn, our E1, E2, I'll make it a set, E3 to En. So I'm going to write that out just so we can talk about it a little bit. 1, 0, 0. Trying to gauge if you're still writing or not, so ignore the silence if you're finished. Okay. We've talked about the standard basis vectors before, and if this is the set of n of them, obviously these are not multiples of each other, right? We've got a 1 in rotating positions as we move through there. And we can get any vector that we want if we use a linear combination of that. So this set of vectors is linearly independent and it spans Rn. So that's what a basis is. You can generate the whole vector space and none of them are multiples of each other. Okay, let's look at another example. Oops, it's supposed to be F equals. So this is a basis for polynomials of degree n or anything less than that. So x squared plus 2x, x to the fourth. It would include lines. 1 plus x is also considered a polynomial, even though it doesn't have a degree more than 1. But you can generate any polynomial that you want from that set, and obviously none of those are multiples of each other. Typically, I would prove that in class, but we're not going to do that. It's not going to hurt you in your future if you don't know how to do that. Okay, here's another example, just to give you some more feel for this, and I might have you do some input on this. So I want a standard basis for matrices that are 3 by 2. What will that first matrice look like?
One, 0, 0, 0, 0, 0.
Yes, thank you. Second one, anybody want to chime in?
Zero, 1, 0, 0, 0, 0.
Good. Okay, get the idea? Now we're going to move the 1 to the second position. Make sure you can still see this. 0, 1, 0, 0. You don't have to write the whole thing out. I think you get the idea. Once again, none of them are multiples of each other, and obviously if we had all 6 of those, we would be able to generate any 3 by 2 matrix that we wanted. So that's the idea behind a basis. Make sure you got that down before I flip. Now, let's try an example where it's not something that's really obvious like that. Okay, so we want to know if this set of vectors from polynomials of degree 2 or less forms a basis for that vector space. Now, it's really easy to think for polynomials, if it's P2, that you only need 2 vectors, but remember that you have, in the standard basis vectors, you would have 1 x and x squared. There are 3 different vectors that you need in order to get polynomials of degree 2 or less. So 3 is a correct number for that. But we want to know if these 3 vectors form a basis. So we need to check 2 things. We need to check to see if they're linearly independent and if they span. So to check linear independence, I'm going to set up a linear combination of those vectors. I just realized I forgot a negative. Go up to the 4 there and put a negative right there. Forgot that. And we want to know if that is, we're going to set that equal to 0 and find out if C1, C2, and C3 have to be 0. So the next thing I'm going to do is write the system of equation that goes with that. It'll be all of the constant values equal to 0. So negative 4C1 plus 6C2 and 8C3 equal to 0. There's the first one. And then I'm going to do the coefficients of x. So C1, 5C2, and 4C3. We want those to be 0. And then we also want the squared terms to have a coefficient of 0. So there's the system that we'd set up. I'm going to translate that to a matrix. And I want to label this so you see where things are coming from. These are the coefficients for C1, these are C2, these are C3. This relates to the constant value, this relates to the x coefficient, and this relates to the x squared coefficient, or coefficient of x squared, I guess I should say.
Is there a reason that the x and the x squared aren't in the like negative 4C1 plus 6C2 or the C plus 5C2?
You mean why we're not putting those in
that left side? Yeah.
in here? Yes, because all we're trying to do is find out what the coefficients of those are.
Okay.
Regardless of the variable expression, we want to find out whether when the coefficient of that would be equal to 0. If I add these 3 together, when will I get a coefficient for the, I'll do the last one. If we take this expression and add it together, when will those coefficients give me a coefficient of 0 for x squared?
Okay.
Does that make sense?
Yeah.
Probably if I write one more step down here. You want me to write this out? Or are you good?
I'm good, thank you.
Okay, all right. Because I can write this out as another, if you write this out one more step and pull the C1 terms together, the C2 terms together, et cetera, it makes a little more sense. Or I should say the x terms and the x squared terms together, it makes a little more sense. Okay, when you put this through reduced row echelon form, hopefully you can still see that. I get 1 0 0 0 0 1 0 0 0 0 1 0. So identity matrix with zeros on either side. That works perfectly, by the way, Claire. So if you guys have questions, just unmute yourself, ask a question, and we're good to go. Plus, it's really nice to have some interaction instead of just me talking. Okay, that means the only solution to the homogeneous system is the trivial one. Which means that theorem that we had is like 4.3.2, I want to say, tells us that that is linearly independent. Okay, now we need to know if S spans P2. Polynomials of degrees 2 or less. And this is actually pretty easy. We've already shown that it does. If you look at matrix A, which is -4, 6, 8. Oops. I want matrix, not determinant. 1, 5, 4, 3, 2, 1. Who can tell me what the determinant is not because of what we got up here?
Not 0.
Yeah, it's not 0. And you can actually go from right here. You can say because this had in reduced row echelon form was the identity matrix, the mega theorem tells us, number one, the determinant's not 0. And for every matrix vector of constants, it has a solution. Okay, the determinant of A is not 0. But you can also say it from up there. REFA implies determinant A not equal to 0.
Can it be linearly independent but not span?
Yes, it can.
Okay.
Remind me if I don't give you an example of that.
Okay.
Write myself a note here and hopefully remember. But I want to get a little farther here before we do that. But that's a great question. All right, hopefully we're ready to go on. I'm going to give you a couple examples here. Okay, some examples of finite dimensional vector spaces. Obviously, Rn is, if you think of R3, three-dimensional, R4, you would know exactly what basis vectors you had for that. Any matrix, any size matrix is finite dimensional, and the number of vectors in your basis is always going to be m times n. And we just looked at Pn, and obviously that was finite dimensional. we will not be working with any of these infinite dimensional ones. In case you have forgotten, this is functions defined on actually continuous functions. So for example, an exponential function, log function, trig functions, those kinds of functions don't have a finite dimensional vector space or finite basis. Okay, anybody have questions before we go on? No, I should say anyone have questions before we go on? All right, question for you. Is a basis for a vector space unique?
No.
Why not, Ethan?
Well, we just showed a basis for polynomials of degree 2
Yes.
that was not the standard basis that polynomial.
Excellent. Yes. The example we just showed, I gave you the standard basis for polynomials. That was right up here. If we wanted to look at the standard basis for polynomials of degree 2, it would be these 3 vectors. But we also showed that the 3 vectors that we did in this example formed a basis. So a basis for a vector space is not unique. That is our next theorem. So a basis for a vector space does not have to be unique. However, any vector in that vector space has a unique representation of the basis vectors. So if you write a linear combination of basis vectors, there's only one way you can do that for each vector that's in that space. We're going to try to prove this. We'll see how it goes. We have lots of V's and going on here. So we have V1 to Vn that are our vectors in our vector space in S, and that's our basis. Capital V is the vector space, and then a small v is just a generic vector that results from that basis. So try to keep that straight. I'll try to make them as All right, we're going to assume. Somebody give me a thumbs up when you're done and I'll know when I can go on. Okay. All right, so that's our assumption. Now let's show that happens. We know S spans all of the vector space. So baby V is expressible as a linear combination. All right, let's do a little bit of a proof by contradiction here. So what we're going to assume is that V can be written as two linear combinations of those vectors and then show that that doesn't work. So I'm going to say that it is C1, V1, C2, V2, etc. And also that it's equal to K1, V1. Well, V is equal to V. So C1, V1, C2, V2 to Cn, Vn has to be equal to K1, V1, K2, V2 out to Kn, Vn. I'm guessing you can see where this is going. I'm going to move all of these over here. So I have 0 on the right side. So C1, V1, C2, V2, etc. And then I'm going to have minus K1, V1. I'm going to factor out, so I'm going to group these two together and factor out the V1. So C1 minus K1, V1, C2 minus K2, V2. And what we have here is a linear combination of the basis vectors. And since it's a homogeneous equation, it's equal to 0, all of these coefficients have to be 0. They're linearly independent, so they have to be, those have to be 0. I've got sun shining right across the side of my paper. Okay, so C1 minus K1 has to be 0. And that's a C. C2 minus K2 has to be 0, etc., which means C1 equals K1, C2 equals K2, Cn equals Kn, which means that any linear combination has to be unique. Questions? We've got one more definition and a couple examples, and we'll call it a day. All right, this one is pretty simple in terms of concept. It's going to take a little while to write out. We've got a set of vectors that's a basis. Okay, that's just the setup. So that's what we're defining. Coordinates of V relative to S. Oops, sorry. Okay, I'm gonna write one more thing down here. Okay, basically what this is giving us is when we make a linear combination of basis vectors, the coefficients of those vectors can be written as a vector like we would think of in Rn. So we're relating every single vector space that we have back to Rn. There's a representation of every linear combination in Rn if you use the coefficients. And we'll look at a couple examples so you see what we're talking about. This right here is V relative to S. So this says the coordinate vector of V relative to the basis S is, and then you list the coefficients that make that linear combination true. Okay, I want to write one more thing relative to this. The order of your vectors matters in this case, in some cases. So typically the order that you list the vectors in set S doesn't matter, but if you're working with vectors, the coordinate vector, like if you're working with V sub S, you've got to know what the order of those vectors is so you know which coefficient goes with which vector. All right, let's start out really easy. Oops, I don't want an S there. This one's so easy, it's hard. What coefficients would I have for those three vectors that would give me 3, negative 2, 5?
Is it 3, negative 2, 5?
Yeah. I'd need C1 times 1, 0, 0, C2 times 0, 1, 0, and C3 times 0, 0, 1 to give me 3, negative 2, 5, which obviously is just 3, negative 2, 5. Okay, this will make you think a little more, not much, but a little bit. Okay, the only thing that's going to be tricky here is the order of these vectors. What would be the coefficient for the vector 1?
9.
Coordinate, or the coefficient for x would be negative 7. X squared would be negative 3. X cubed, there isn't one, so it would be 0. And then x to the 4th would be 4. So this is the coordinate vector of P relative to our basis. All right, last example.
We can't see the video.
What happened? Oh, somebody's trying to call me. Sorry. Let me shut it off. Somebody from Texas is trying to call me. There we go. Thanks for letting me know that.
They're apparently persistent. We've lost video again.
Second. All right, give me a second. I got to join the meeting again. Drat. We were almost done too. Now I got to let myself back in. I keep getting stuff coming up. Try that again. All right, flip my camera. There we go. All right, find the coordinate vector for A equal this. I gotta put my last.
Pin the doc cam.
Yes. What about it, Sarah?
Can you pin it? It's
Oh, yes, sorry. Forgot I had to redo that. Thanks for reminding me. There we go. Okay, so A, I'm gonna write, I think I'm forgetting parentheses. There should be parentheses around that. It should be A sub S. All right, so our first basis vector would be a 1 in the upper left-hand corner and zeros elsewhere. So it would be 1. Second one would have a 1 in this position. So we'd have 0, -3, 2, -2, 1, 5, -4, and 0. So all we're doing, the standard basis for this would be 3 by 3 matrices, and you just rotate the 1 across the first row, across the second row, and then